Okay. So in the last class, we were discussing about the genetic parameters. Okay, the three important genetic parameters, and we have discussed about the heritability. As I told you, there are three genetic parameters. Those are your heritability, repeatability, and the genetic correlation. Okay, so heritability part we have discussed, and to understand the things, we have started from the variance. As we know that the phenotypic value, the earlier classes, the phenotypic value, it has different components. That is your genotypic, then environmental components, then the your genotype, environment, interaction, all those things, different components we have discussed. And those values we can express in terms of the variance, that is your phenotypic variance. Instead of the phenotypic value, we can assign as the phenotypic variance, then the genotypic variance, then the genotypic variance we have divided into different components again. It has additive, dominance, and interactions. So these are under the genotypic variance. So these things we have discussed. Or additives, dominance. Can you see the cursor? The cursor, can you see?
No, sir.
Cursor is not coming there. Oh. Okay. Okay, anyway, the phenotypic variance, it has different components like your additive component. This additive component is also known as the breeding value, okay? Then dominance component, then interaction component, gene interaction component, then the environmental component. Then environmental component, and there may be genotype environment interaction, that is GE interaction, that is we call it as the genotype environment correlation, okay? That is expressed as twice covariance of GE interaction. Then one more is there, that is genotype environment interaction. Okay, so these are the different components of the variance. And regarding the heritability, as we know that all these components, your A, D, I, E, this correlation, interaction, all these components, are they going to inherit to the next generation or not? Okay, that is the question. Okay, so that what part of these components is going to be transmitted to the next generation? That is we call as the heritability. Remember, heritability is the out of this phenotypic variance, the fraction of the total phenotypic variance which is due to the additive genetic source. That is we call as the heritability in the narrow sense. Then heritability in the broad sense, also we have described as the fraction of the total phenotypic variance which is due to the genotypic variance. Okay, this is we call as the broad sense heritability. And you know that this genotypic variant, this many components, but all of these are not going to transmit to the next generation. That's why this is not the true sense heritability. The true sense heritability is your narrow sense heritability. And we have discussed about the range of heritability. The heritability range is 0 to 1. And these things we have discussed. And some of the examples, the heritability values, as I told you, for the production traits, the heritability value will be medium, and for the reproductive traits like conception, rare, and those things, the heritability value will be low. As you can see, it is 0.01, and the morphometric traits. Okay, morphometric traits, the heritability value will be high. Okay, so high, low, medium. You used to remember it. Then the estimation of heritability we have discussed the heritability estimation can be done in many ways: half-shift analysis, full shift, variant offspring correlation, regression offspring, then selection. Yes. Yes, any problem?
Sir, the slides are not moving.
This is the problem every time. Let me check once.
So now it's okay.
Now it's okay, no? Let me check once. Now, is it moving? Importance of heritability, is it coming to your screen or not? Importance of heritability. Yes. Is it moving or not? No.
No, sir.
Then I will not put in the presentation mode. Okay. I think this is okay. It is moving, right? Is it moving?
Yes, sir. Yes, sir.
Okay. So this part we have already discussed in the last class. So and remember this in the half-shift method, the calculation we are using analysis of variance. Okay, that is we call as the ANOVA. And remember this thing, same thing will be using in the repeatability also. This is we call as the interclass correlation method. Okay, interclass correlation method, and this will be using in the repeatability also. So let me skip forward shift regression method, and okay, that is all about the heritability. And sorry. Okay. So we know that the heritability deals about the transmission of the genes or the transmission of the characters. Okay, how much of the character will be transmitted to the progeny? That is measured by the heritability. And now, like some of the traits, some of the characters, they express repeatedly at different time intervals in the same individuals. No, there are some repeated traits which express at different time intervals in the same individual. Can you tell me some traits or the characters which express repeatedly in the same individual at different time interval? Yes, anyone? Some repeated traits like your lactation, the milk yield at different lactation. So you have different lactations, no? In between different lactation, there is some gap, right? There is that period is there. Then the milk yield start again. So like that, no. So it has different periods. It expresses repeatedly at different time intervals. Okay, so milk yield, the first lactation, the second lactation, the third lactation. So like that, at different time intervals they express. Okay, that is we call as the repeated trait. And in the case of the pig, like farrowing, the litter size in the farrowing. So in the first farrowing, you may have say 10 piglets. The litter size is 10. Then in the second farrowing, what will be the number? The same 10 will be there or not? Okay. And third farrowing, the same litter size will be there or not? That will be measured by the repeatability. Okay. the repeatability will measure the those repeated traits. So to express, yes, I told you there are traits or characters which can be measured more than once in the individual's lifetime, like your farrowing, the milk production, that is okay. And this repeatability is the correlation among the multiple measurements of the traits in the same individual. Okay, it is the correlation among the multiple measurements of the traits in the same individuals. And repeatability refers to the of expression of repeated measurements of the same trait at different times in the life of the same individual. For example, the milk production, as I told you, the fleece parameters, the litter size, etc. Okay, that is repeatability. Or in other words, it is regression of the future records on the past. Okay, the regression of the future records on the past. Okay, in the past, in the first following, say animal is giving the litter size is 10, suppose 10 piglets. In the second lactation, how much it would be there? Okay, that the repeatability value will tell you. Okay, the term repeatability was given by Lurs in 1945. So for such repeated trait, the total variance can be partitioned into two components. Okay, one is variance within the individuals, another is variance between the individuals. So the variance within the individual is due to the temporary environmental variation. So see, in the first lactation, the average milk yield is this much. In the second lactation, the average milk yield is this much. Is the genes, the genotypes responsible for that? There is variation. Okay. Even in the litter size also, there is variation. Sometimes 9, 10, 7, that variation is there. Okay, the same trait measured at different time intervals. There is variation. In the milk yield also, first lactation is different from the second, and second is different from third. There will be difference. So what may be the cause for that variation? The same individual, the genetic makeup is all the same, right? Whatever the gene the individual has at the time of the birth, it will remain. Is it? There should be some interaction, otherwise it is very one-sided. Okay. So whatever the genes you have, whatever the genes you have, okay, will it be changed in your life or not? That is the question. The genes you have is not going to change. Okay. But why there is variation? The problem is that today animal is producing this much of milk, and tomorrow the animal may produce some different amount of the milk. Why there is variation? Though the animal has the same the genetic makeup. So that is mainly due to the environmental component. As I told you, the phenotype, it has genotype and environment. Huh? So genotype is same. The individual will have the same genotype, but that environmental component, it is making it different. Okay, so that is we call as the temporary environmental variation. Okay, the variation within the individuals. In the first farrowing, the 10 liter size, 10 piglets, second farrowing, 12 liter piglets. That variation is maybe due to the temporary environmental variations. We call it as the temporary environmental variation. And the variance, the variation between the individuals is due to the genetic and partly due to the permanent environmental factors. Okay, between the individuals. Okay, between the individuals there may be some difference. Okay, this sow you have sow X and Y. There are two sows, and the sow X, their performance may be different from the other sows because they are genetically different. Okay, that is one factor. And other factor is due to the permanent environmental factors. Suppose, for example, in one sow, there is, there is some anatomical defect. It may cause the permanent effect on the animals. Okay, say one sow is having some problem, and other is not having some, and other is not having any problem. So that may also cause a difference. So between the individuals, it's due to the genetic as well as the permanent environmental variation. Whereas in the case of the individual case, it is surely due to the temporary environmental variations. Okay. Thus, the fraction between the individual variance of the total phenotypic variance is the interclass correlation that we have discussed in the heritability also. So the interclass correlation, that is here VZ plus VEP. VEP is nothing but this is the permanent environmental, and ET is the temporary environmental variance. Okay, this all together is the total phenotypic variance. Okay, so out of this phenotypic variance, you have VG plus the permanent phenotypic variance. This ratio is we call as the repeatability. And the difference here with the heritability, what's the difference? So these environmental components, okay, here, up here, the permanent environmental difference is permanent environmental variance is included here. Okay, that is the difference. And that is why repeatability is called as the upper limit of heritability. Okay, upper limit of the heritability, we can say like this: the denominator is we express as the phenotypic variance. So this ratio is there, and VG by VP is nothing but the heritability. Remember the heritability in the broad sense, and this component is the extra one. So that's why this is the repeatability is called as the upper limit of the heritability. Okay, upper limit of the heritability. So its value is bigger than the heritability. You can see from here, since it includes the environmental, permanent environmental factors. Then some properties of the repeatabilities are the value of repeatability also ranges from 0 to 1. Remember, 0 to 1, like your heritability. And it is also the property of the thread. Okay, from thread to thread, character to character, there will be differences. Like heritability also, there is difference between the different traits. And it's about the property of the population. And population to population, there will be some difference. Okay, herd to herd, there will be difference, like your heritability. It is also the property of the environmental conditions, and it depends on the environmental conditions. Okay, these are some of the properties of the repeatability. Then importance of repeatability. As I told you, it sets the upper limit of heritability, and it is used in determination of gain from the multiple measurements. If we use the multiple measurements, how much gain it will be there, then we can use, we will see later on. And it helps in prediction of the future performance from the past record. Okay, prediction of the future performance from the past record. And it also has in the estimation of most probable production ability. Okay, MPPA. This is very important parameter. You will see later on. So and the estimation of R, it's much easier than heritability as compared to the heritability, since heritability requires different generations, okay? The parent generation, then the offspring generations. Whereas in the in the repeatability, you have to see in the same generation, okay? So it is much easier as compared to the heritability. Therefore, this repeatability can be used as a preliminary genetic information about the heritability in the conditions where heritability cannot be estimated due to lack of information on a group of relatives. When the heritability value is not available, then you can use the repeatability value, okay? It will give some idea about heritability in the population. So then, gain for the multiple measurements, genetic gains. Repeatability indicates the gain in accuracy expected from the multiple measurements. If you are taking the multiple measurements, it will give you the accuracy in the gain, genetic gain, okay? By repeated measurements, the environmental component is reduced. Okay, if you are taking the repeated records or measurements, the environmental component is reduced, and the heritability is given as this formula. So here in this case, if the heritability value is high, if the repeatability is high R means little gain in accuracy from multiple measurements. So now you can decide we need to take the multiple records or not. The knowledge of repeatability is useful in selection programs to know the relative efficiency of using a single or multiple records. So if the R is high, there is no need to take the multiple measurements. Okay, and if it is low, then a more gain accuracy will be there for multiple measurements. Okay, it will decide the value of the repeatability will tell you whether we should take more measurements or not. Okay, that is one important importance of repeatability. And another is the prediction of the future performance from the past records. So this repeatability R is used in the selection for the better performance in future by estimating the producing ability. Okay, R is required to predict the producing ability, like heritability is required to predict the breeding values. In predicting the breeding values, heritability is required. So like that, this repeatability is required to predict the producing ability of the animals. Since R is the correlation between the two performance, X and Y. Okay, R is the correlation between the repeatability is the correlation between the two performance. So X and Y means the first farrowing and second farrowing. Then the prediction equation we can draw like this. Okay, this formula you can say here the high R means single record is quite enough to predict the real producing ability. Okay, if the repeatability is high, then the single record is quite enough to predict the real producing ability. That is, culling on the basis of the single record will be effective. And low repeatability means culling should not be done on fast record only. Additional records it's important because a poor past performance may be due to the temporary environmental effect which is not carried out. So the simple thing is, if the repeatability is very high, the value of repeatability is very high, then you can select or you can predict on the basis of the first record. Okay, the fast following record say fast following records that the animal the litter size is 12 piglets. So if the repeatability is high, then you can expect that in the second following also you may get near around the same number of the litter size, 12 numbers. Okay, that is the importance. Once we know the repeatability, then you can select the animal on the basis of the first record. No need to wait for the second or the third multiple measurements. Okay, that is the importance. And another is most important utility of the repeatability is to calculate the most probable producing ability. Okay, the most probable producing ability, that is we call as MPPA. It is also known as the real producing ability given by the J.L. Lewis in 1945. Say for comparison of different cows having different number of records, okay, you have different cows having different number of records. So J.L. Lewis used this relation to predict the most probable producing ability for the dairy cows to adjust the different records on the same basis. Say this is the formula for the most probable producing ability, MPPA. So here, this H bar is hard average, then the individual average is the number of records, the repeatability of the traits. So R. So lifetime average, which shows the ability of the certain individuals to repeat a high level of performance over a long period of times, are very important in animal breeding. So in calculating the MPPA, this R is an essential component. Okay, it is an essential component. So so this is one important utility of the repeatability. Okay, these four are the importance of the repeatability. Okay, remember. Then regarding the examples of some MPPA, say as the number, this is number of the records increases. Okay, the accuracy will keep on increasing. Okay, if you are using only one record or one measurement, then you're getting this much of MPPA. But as you increase the number of the measurements, okay, the accuracy of the prediction will be increased. Okay, the estimation of MPPA will increase. Okay, this is. So these are some of the repeatability. Say like lactation milk yield, repeatability is 0.4, the fat percent 0.6, like fat yield like this. Okay, for the different period. Then calving interval, this for this one also for the reproductive traits like heritability, the value is low. Okay, 0.01 to 0.16, they have low value like heritability. Okay, these things. Then regarding the estimation of repeatability. So while estimating the repeatability, there are two assumptions. Two assumptions are there for estimation of repeatability. One is multiple measurements should be of genetically same. Okay, one assumption, they are genetically same. And different measurements should have same variance. It has same variance. So for any ANOVA, like it has same variance, this and that, this is the assumption. Okay, for any ANOVA test, this has to be done. Then method of estimation here. There are two conditions. One is at least 2 records per individual are required for each estimation. Okay, this is one thing. At least 2 records per individuals are required for estimation. And the methods of estimation of R is basically depend upon the number of records per individuals. Say if you have only 2 records for individuals, so first and the second lactation records only. Okay, you have the records for the first and the second lactation only. Then you have to use the regression method or the correlation method. Okay, if you have only 2 records, then you have to use regression method or the correlation method. And if you have more than 2 records per individual, then you have to use interclass correlation method like that of the half-set heritability, the ANOVA method. Okay, that is. So these are the methods. And the regression method, it is the simple regression coefficient. Regression is done by later future record on the earlier record. Okay, so the regression formula, this is a regression formula. This is known to you. Okay, this is how we can calculate by the regression method if you have 2 records only. Then so for example, lactation 1 and lactation 2, this cow 1, the milk yield is given. So from here you can find out. Then the correlation method, so this one also it is used when you have only 2 records. Okay, it is simple correlation coefficient method, and this formula is the simple correlation, okay, formula. So you can apply this formula and you can find out the correlation, the repeatability using the correlation method. And this interclass correlation method, like that of the heritability, so the same procedure you have to use. Here is like when more than 2 records per animal are available, then calculation of the correlation coefficient becomes laborious because it has to be estimated in all possible combinations. Like you have in the earlier, or if you have only two records, X and Y, then you can directly do X and Y. If you have more than 2, then you have to do all the possible combinations, okay? 2 combinations if you want to use the correlation coefficient method. So that is very laborious. So in those cases, you have to use ANOVA method, as in the pattern halves method we have used earlier in the heritability. Okay, the same method you have to use. It is used to the it is similar to the method of estimation of heritability by half-set correlation method. The steps are to be calculated of T as in the heritability. You can go back to the heritability and you can see how the T is calculated. This T is nothing but interclass correlation. How it is calculated, that you can see later on. And this repeatability is equal to your interclass correlation T. Okay, this is okay. That is all about the repeatability. Now coming to the last genetic parameter, that is we call as the genetic correlation. See, if you see in farm animals, most of the economic traits are correlated with each other to a certain extent. Okay, to a certain extent, they are correlated to each other. Okay, most of the traits. Hence, in a population, any 2 quantitative characters may have the relationship either positively or negatively in the individuals. And the correlation coefficient, the calculation is the same. This is the same formula used in the regression also, and there also in the calculation of heritability also. Okay, same formula. So, like, it may be phenotypic correlation, then genetic correlation or inheriting correlation. Okay, there are 3 types of the correlation. So the phenotypic correlation is defined as the correlation between the observed, okay, the correlation between the observed phenotypic values of the 2 characters. It's the correlation between the observed phenotypic values of the 2 characters. Okay, you have 2 characters, X and Y. So that correlation is we call as the phenotypic correlation. Okay, based on the phenotypic values. And this is the formula you can use for the phenotypic correlation. And the phenotypic correlation, okay, so say suppose the milk yield and the fat percentage. If we increase the milk yield, the fat percentage will decrease. Okay, why there is a simultaneous change in the character, both the characters? Either it's synergistically in the same direction or in opposite direction. Why there is? Okay, it may be due to the, it is due to the genetic correlation. One is, okay, another is environmental correlation. Okay, whatever the phenotypic correlation is due to the genetic correlation as well as the environmental correlations. And the genetic correlation, okay, it is the correlation of the breeding values of the two characters. It is defined as the correlation of breeding value of the two characters. The breeding value, whereas in the case of the phenotypic correlation, it is the correlation of the phenotypic values. Okay, here in the case of the genetic correlation, it is the correlation of the breeding values of the two characters. Okay, remember. Or between the sum of the additive effects of the genes influencing these two traits. Or it is the correlation between the sum of the additive effects of the genes, influencing these two traits. Okay, so you note that this additive effect is nothing but the breeding value. Okay, however, there are others also, such as the correlation between the genotypic values and the correlation between distribution, that is of less important here. Okay, now the question is, what may be the causes of your genetic correlation? Okay, say the causes of genetic correlation. As I told you, if the number, if the milk yield is more, then the fat percentage or the butter fat percentage in the milk will be less. Okay, so there is some correlation. If the milk yield is increased, then fat percentage will decrease. So some correlation is there, right? So why there is simultaneous change in water characters? What could be the cause for that correlation? Okay. So there are three possible causes. One is the pleiotropic genes, another is the link genes or the linkage, and another one is heterozygosity. These are the three possible causes. And pleiotropic genes. Pleiotropic genes, what is that? Can anyone tell me? What is pleiotropic genes? He says Jordan. This is Jordan. Yeah,
Yes,
can you
sir.
tell me what is pleiotropic genes?
Sir, it is a single gene that controls more than one trait.
Okay, very good. So if the same gene, pleiotropic gene, as she told, is if a gene is or if a gene is involved in the expression of more than one characters, they are we call as the pleiotropic genes. And opposite to the pleiotropic gene is your polygenes. Remember, polygenes means for a particular trait character, many genes are involved. Okay, this is just opposite to the pleiotropic genes. So if the same gene is controlling your milk yield and the fat percentage, okay, if you have a gene, that particular gene is involved in the expression of the milk yield as well as the fat percentage. If there is some change in that gene, both the character will change. Is it? Both the characters will change. Okay, so that's why these pleiotropic genes are the main cause of the genetic correlation. Okay, in the genetic correlation is nothing but both will change. maybe in the same direction or in the opposite direction. Okay, that change, if the same gene is controlling both the characters, if there is some change in that gene, both the characters will change in the expression. Okay, that is pleiotropic genes. Okay, this is the main cause for the genetic correlation. And there may be negative genetic correlation. Negative genetic correlation means it is the antagonistic effect of pleiotropic genes, that is, they act in the opposite direction. For example, as I told you, milk yield and the fat percentage. Okay, they move in opposite directions. So it may be negative or it may be positive. Okay, positive, can you tell me one example? Anyone? The height and the body weight. This is also a positive correlation. Okay, if the height is more, then weight has to be more. Okay, that is positive correlation. Then linkage is another cause. As we have discussed in the case of the linked genes, if the genes, say, suppose the gene for the milk yield and the gene for the fat percentage, if they are located very close in the chromosome, or if they are present in the same chromosome, then that is linkage. No? If they are present very close to each other, then your Mendel's laws, your law of segregation, law of independent assortment, those things will not follow, okay, if they are very close. Because to follow those things, there has to be crossing over and all those things has to be there. And if they are very close, then the chances of crossing over taking place, separating those two genes is very less. So always those two genes will be present together. Okay, always those two genes will be present together. Okay, if they are closely linked, because there is no chances of recombination or the crossing over taking place between two genes, those two genes. Then in those cases, always these two characters will inherit together. If there is something change in one gene, then other one also will change. Suppose you have two genes, A gene and the B gene. So A1 and B1 are always together. Okay. If A1 and B1s are always together, then A2 and B2 will be always together. So instead of A1, if A2 is there, then definitely 2 from B1 to B2. Okay. So that may be also one cause of the genetic correlation. Okay. This is. Then another one is, as I told you, heterozygosity. Heterozygosity is like if the genotype is heterozygous, the chances is that you may get the hybrid vigors. You know what is hybrid vigor? Hybrid vigor means those hybrids, not the heterozygotes, their performance or the expressions is always better, in most of the cases, better than those of the homozygotes. Okay, say A1, A2, this heterozygote A1, A2 is better than your A1, A1 or A2, A2. That is we call as the hybrid vigors. Okay, the heterozygotes, due to the interaction between A1 and A2, they may perform better. So if there is hybrid vigor in one character, the heterozygous condition is there. So it has the hybrid vigor. It has a superior performance. Then what happens is the other nearby characters, the superior performance in one character influence the other nearby characters also. to perform better. Okay, it influences other nearby characters also to perform better. That is heterozygosity. Okay, so like you have different types of the friends, different types of the peoples are there. If you are with the good friends, very intelligent, good friends, then your character may also change and you may also start performing better. Okay, it may influence, your company may influence you. So that is something, it happens physiologically in the body also. If a character is performing better, superior, so it may influence other nearby characters to perform better. Okay, that is we call as the effect of the heterozygosity. So this may be also one cause for the genetic correlation. Okay, remember these three causes. Then the environmental correlation. Sometimes what happens is the correlation between the environmental deviations may be there. It also includes the correlation due to the non-additive genetic deviations. Non-additive genetic deviations. Okay, it may also include. It arises from common environment shared by two characters. Let us see. Two characters are influenced by the same difference of the environmental conditions, common environment. Okay, two characters are there. It may be influenced by the same difference of the environmental conditions. Okay, so let's suppose character one milk production and character one is milk production, character two is the fat percentage. So sometimes the same environment or the different environments or a particular environment may influence both the characters. Okay, both the characters. Then in the different environment, the both character will change. Okay, it may happen. So same thing, the poor nutrition to a young lamb, it results to the poor growth, resulting into poor wool yield. Okay, poor growth. If the poor growth is there, then it will result into the poor wool yield. Okay, this is one example. And you know that this correlation caused by the environmental effect is not inherited. This poor nutrition, it may change from time to time. Next time we may be giving